think everyone's in the room now. We're very privileged to have David Jamieson, Professor David Jamieson from University of Melbourne. We've made him our keynote speaker and given him a full hour so he can do a proper presentation and doesn't have to squeeze it into half an hour. I've told him that we have keyed up amateur astronomers who have a good appreciation of the solar system and all these spacecraft going out, and to throw in a few equations and not be scared to ramp it up. So you're going to blame me, aren't you, if he gets too heavy? But I've told him just to judge it and wing it and ramp it up or down as he needs. How long have you been with Melbourne University, David?
I've been with Melbourne University for a long time. I started in my job as a lecturer in 1989.
Oh, wow, a long-time resident. That's good. I was reading on the website about 100 people in physics at Melbourne Uni, is that right?
We've got about 100 PhD qualified staff in the building,
yep, and
about 100 PhD students and nearly 1,800 undergraduates.
Fantastic. That is stunning. I won't delay by holding him up. Dr. Professor David Jamieson. Thank you.
Well, Ken, thanks very much, and it's always a pleasure to have an opportunity to speak to an enthusiastic audience like this. I must say that I'm not a professional astronomer, and my interest in Mars and the Curiosity rover is through the physics, but also from the excitement this generates amongst the public and amongst our students. And so I have, over the past couple of decades, given various public lectures on different aspects of Mars as the remarkable avalanche of data pours back from all the space missions. So what I want to do today is start off by giving a bit of a recap on what we know about Mars, and then in the second half talk about the physics of the Curiosity rover, because this is a fantastic machine that's now roving about in the Gale crater. And we're finding all sorts of amazing things about Mars. To avoid suspense, the discovery of water on Mars has now been replicated about 1,000 times from different experiments. And so it's a bit of a joke apparently amongst the scientists that we've discovered water for the 1,000th and first time every time new data comes in. So plenty of water on Mars, but not, of course, in the liquid phase. That's not possible because of the atmospheric conditions, but we'll come back to that. So you've been looking. Can I take the lights off for this one to increase the drama of this fantastic image? Okay. And also because it's a special occasion, I'm using my special short wavelength laser pointer for you. So this is the view from near the centre of the Gale crater on Mars from the Curiosity rover, looking back towards the walls of the crater. This is an immense crater that was most likely an ancient sea 3 billion years ago. And it's hard to see in this room with these lighting conditions, and I've chosen to use the image that hasn't been processed. So this is what you would see with the unaided eye if you were standing in a suitable spacesuit and looking towards the crater yourself, because the Mars is further from the Sun, the Sun is dimmer, and the light is pinker because of the characteristics of the Martian atmosphere. Very thin atmosphere, but you can just barely see in this image this zigzag that looks like a road switchbacking down the walls of the crater. This is in fact an ancient river that used to feed into the water that almost certainly existed here 3.5 billion years ago. So before I get into Mars, I want to just come back to Earth for a moment, because you might be wondering who I am and what I do in my day job. And as I was saying to Perry just before we started here, my group is involved in the construction of a revolutionary type of computer called a quantum computer. And over the past 2 years, we've had a series of remarkable breakthroughs. And I just wanted to inject one slide on my research and then we'll get back to Mars. But this is a microelectronic device, or more particularly a nanoelectronic device, where we in Melbourne insert a single phosphorus atom into this crystal of silicon, represented by this blue dot here. And then it's configured with suitably tiny transistors and electrodes, and we're able to program the nucleus of the single phosphorus atom in this block of silicon. And just recently we showed that we were able to take the nucleus of the phosphorus atom, and it's spinning like a top, and sometimes it spins with the axis up and sometimes with the axis down, and by the mysterious laws of quantum mechanics no other alternative orientations are allowed in nature. And by carefully bombarding it with microwaves fed down this aluminium wire and holding this whole thing at a temperature of a few thousandths of a degree above absolute zero, we were able to make the nucleus spin up and down simultaneously. Yeah. So don't try and understand that. Come along and enrol in our subjects at the university and we'll explain everything there is to know about it as far as humanity is able to come to terms with the shocking truth about the way the world works at the fundamental level. But this allows us to program information onto this nucleus spin, and unlike a classical computer where each bit is 1 or 0, in this quantum computer each bit is a quantum bit and is 1 and 0 at the same time. And this unlocks an enormous potential by harnessing these strange attributes of the quantum world. And just to give you an idea, this is about 10 million times actual size on this screen here, maybe only 5 million times in this theatre. Usually I have a bigger screen. But just to give you a comparison, this is a polio virus on the same scale. So this is a very tiny device and sensitive to the attributes of just a single atom that we put in. Anyway, back to Mars. So I want to just start with a quick history of Mars, because Mars has always loomed very large in human imagination. And it seems that we've been going to Mars for thousands of years in our imagination. And I have a very small collection of science fiction, or a very large collection of science fiction books, and a substantial fraction of them deal with Mars. And it's always portrayed, at least up until the Mariner expedition in the 70s, hence from the name, of course, as a warlike place. You always have swords on Mars. And in fact, this book, not only they had swords, they had green laser blasters. And I just don't know why they kept using swords, but it just seemed logically inconsistent if you had a green laser. And of course, Edgar Rice Burroughs' John Carter series, that was a terrible movie. Don't go and see it. I don't recommend it. It came out last year or the year before. And of course, we've always felt that Mars was going to invade. Sinister aspects of Mars very evident in the literature. And then there was a more sort of poetic version of Mars around the middle of last century, most notably the late Ray Bradbury, and of course the somewhat meta-theological stories of C.S. Lewis portrayed a sort of softer, mystical version of Mars. Some of us were influenced by these stories in our childhood. But the reality is very different. We see a rather alien world. And the true nature of Mars emerged very slowly, because it's obviously very small and very far away. And as far as I can tell, this is the first observational data on Mars that resulted in features from Huygens in 1670. And then, of course, we had the channels that were observed by Schiaparelli that morphed by Lowell into canals, obviously built by a dying civilization on a world suffering major climate change where the planet was drying. And these very detailed maps of these canals began appearing in the literature. And Lowell did publish in the serious literature, and I've delved back into old copies of Nature and dug out the journal Nature, and dug out some of his early papers. And he's very earnest and sincere in describing these very intricate patterns of what he called canals that he could see through his telescope. Galileo too, was one of the first the first telescopic observer of Mars, but there were no features observable on the image of Mars that he could see in his telescope. The magnifying power was insufficient. But the telescopes got better on Earth, and more high-resolution images began appearing up until we visited it with space probes. The evidence for the observational evidence for intricate patterns of canals gradually faded, and now we realise that these were optical illusions and they existed in the mind of Lowell, not on the planet itself. And I found this very interesting book on iTunes by Alfred Wallace, who wrote this fascinating monograph titled "Is Mars Habitable?", a critical examination of Professor Percival Lowell's book. And he goes through carefully, using sound reasoning based on the laws of physics, to examine whether it was possible to have a canal that went from the pole of the planet to the equator, because that would imply a surface topography that had to be incredibly smooth in order to build this canal. And he analysed how much Earth would have to be moved and what the fall would have to be. But even more particularly, he analyses whether it was possible to have liquid water on the surface of Mars. And this analysis must have been informed by the paper that was published by Saventi Arrhenius around the same time, where Arrhenius for the first time realised the importance of the greenhouse effect in determining the temperature of planet Earth. Because as you probably know, if we didn't have an atmosphere, the average temperature of the surface of the Earth would be about 15 degrees below zero. That's the heat delivered by the sun to the surface of the planet. But we now know, of course, or we obviously know, the average temperature is more like 15 degrees above zero, because there's 30 degrees of global warming contributed by the greenhouse gases in the atmosphere, principally water vapour. 30 degrees of global warming from the atmosphere. But on Mars, this phenomenon cannot occur because the atmosphere is too thin and the greenhouse effect is very weak. Despite the fact, of course, it's made of carbon dioxide, as we will see, and like on Earth, carbon dioxide contributes to the greenhouse effect, but only to a small extent, only a few degrees. And Arrhenius pointed this out at about 1880, I think, or 1890, when he published his paper. From the vantage point of northern Sweden, he predicted that it would take humanity 3,000 years to double the carbon dioxide in the atmosphere of the Earth, and that could be good for Sweden because it would make the temperature go up 4 degrees. And in the past 130 odd years, nothing has changed, except the supercomputers have refined it from 4 degrees to 4.2 degrees or something, because we've got 30 degrees from water and another 4 or 5 degrees from carbon dioxide, and that's what we should be worried about. And I'm dwelling on this because the Earth crossed the Rubicon last week, when for the first time in 3 million years the concentration of carbon dioxide in our atmosphere topped 400 parts per million. That's a really remarkable record, considering that when I started my job as head of physics, the concentration of carbon dioxide in the atmosphere was only 385 parts per million, and that was 2008. So I personally don't think we should be doing this experiment with our atmosphere, but anyway, we are. So this brings me back to Mars now. So Mars has been the subject of intensive investigation. Some say this article in Scientific American a few months ago criticised NASA for its obsession with Mars. This diagram shows the number of space missions targeting Mars in the last 20 odd years, and you can see there's a lot going to Mars. There's a couple to the Moon, one to an asteroid, Jupiter, Saturn, even Pluto gets a mention. One lonely mission down to Mercury. Very hard to get to Mercury from the Earth. But you can see there's a planet missing here, Venus, completely absent. But the imperative to study Mars is Mars can provide a lot of insight into the origin of life on the Earth and, of course, climatic conditions on the Earth. And so it's been bombarded with this array of rovers, the Sojourner and Spirit and Opportunity, of which Opportunity is still going. Spirit got bogged in a sand dune and ran out of power and is silent, but Opportunity is still going nearly 10 years after it touched down, which is a remarkable record. And this was never designed to happen. It was thought Opportunity and Spirit would last only a few months, but by a remarkable phenomenon, whirlwinds sweep across the rovers from time to time, cleaning the solar panels. And so, the power gradually fades as dust and dirt builds up on the panels, and the rover grinds to a halt, and then you get a whirlwind blow across it, and it comes to life again and keeps going. And that's been the cycle for 10 years now for Opportunity, if they don't get it bogged. But of course, Curiosity is a monster compared to these previous ones, the size of a small car, has already started. It's been down since August last year. It seems to be moving more slowly than Spirit and Opportunity did, but it seems to be working well. A few minor software glitches, and I'm sure these aren't Martians. This was taken on Earth, obviously. So, getting back to one of the first images of the Gale crater, if you really were standing there and looking out with your own eyes, it wouldn't look entirely like this, actually, because the atmosphere of Mars is very thin, and there's a strange phenomenon which I'll come back to, which you would observe. But let me show you a few more photos. If you zoom in on the wall of the crater, there's a lot of volcanic ash and other debris, and you can see layering in the walls of the crater. This image has been recoloured as if it was being illuminated by the sunlight we experience on Earth. So this is more the true colours that we're used to. And there's a mountain in the middle of the crater which Curiosity will head towards, and this mountain consists of strata in the Martian crust that's been exposed by the ancient meteorite impact that it hopefully will reveal the geological or aerological history of the planet as one of the primary destinations for the rover. And you can see already in these telescopic views from the landing position quite remarkable bands of terrain here. It's almost certain that some of these strata were laid down on the bottoms of ancient oceans, because it's very difficult to imagine how these regular layers could be formed in any other way. But when the rover gets closer, we'll get the chemical composition and we'll find out exactly what's going on. So, with that quick overview, let me now turn to the history of the planet. It's very nice to have two neighbouring planets in the Goldilocks zone of our solar system, that is to say, the zone where life could exist. And these three planets, Venus, Earth and Mars, have obviously had different histories associated with them. The conditions on the surface of each of these three planets couldn't be more different, despite the very similar environmental solar system speaking conditions. The single most distinguishing difference between our three planets is the composition of the atmospheres. Both Venus and Mars seem to have relics of the original atmosphere that would have also been on Earth when the planets condensed out of the protosolar nebula, namely a thick carbon dioxide atmosphere with a bit of nitrogen and maybe a little bit of water vapour. But now Earth is distinguished by the fact that the original primordial carbon dioxide has been removed from the atmosphere and put into the crust of the planet. And that, of course, has been done by 3.5 billion years of activity by life itself. And the waste products from that process is the oxygen which is now a significant fraction of our atmosphere today. So the atmosphere of the Earth is very unnatural, but life is natural, I suppose. But if you see what I mean, really the carbon dioxide has gone, and this would be quite mysterious to anyone studying our planets from outside the solar system. They'd wonder where the heck the carbon dioxide had gone and where did all this oxygen come from, because oxygen is a very poisonous gas and oxidises things, and this is clearly some strange process at work. But as I said, studying our three planets helps us get better insights in our own, because these act like two different planetary laboratories where different experiments are running, and you can see the outcomes and to understand the mechanisms. Not counting the experiment humanity's running on its own biosphere right now. So if we look at the composition of Mars and Venus atmospheres, you see the mostly carbon dioxide, overwhelming majority, a little bit of nitrogen, a little bit of argon coming from the radioactive decay of potassium in the crust, tiny amount of oxygen on Mars, we're not sure about Venus. A little bit of methane on Mars. This created a lot of excitement when methane was detected in the Martian atmosphere, because methane has a relatively short half-life in the atmosphere because it gets broken down easily by sunlight, and therefore the presence of methane suggests it must have a continuous source from somewhere. And on Earth, of course, that's the belching of cows and other macroorganisms. And so this would suggest that there's some organic activity on Mars that continually replenishes the atmospheric methane. I think now that a natural process has been proposed that does account for this very low concentration of methane, so it may not be life, or at least not life as we know it. So remarkable similarities despite the very dramatic differences in the amount of atmosphere between Mars and Venus, but this is the signature of planets with no life, namely the domination of the original carbon dioxide atmosphere. The other remarkable things about comparing Earth and Mars is very small. It's only 10% of the Earth's mass, about half the radius, and you'd only weigh about a third as much on the surface as you do on the Earth. But the atmosphere is incredibly thin, only a hundredth or a thousandth of the Earth's atmosphere, and the pressure does vary dramatically from place to place, unlike the Earth, due to the extremes of the Martian climate, when some of the atmosphere actually freezes out onto the ice caps during either the northern or southern hemisphere winters, which doesn't happen here on Earth. And this very thin atmosphere doesn't support a substantial greenhouse effect. And furthermore, the gravity of the planet, given the average temperature of Mars, is too low to hang on to an atmosphere of water, vapour, carbon dioxide and nitrogen. The atmosphere of Mars for the last 4 billion years has gradually been leaking into space. And that's because at a given temperature, we've got molecules of the atmosphere in this room zooming around at high speed, and a whole lot of different speeds. Some are going fast, some are going slow. They're colliding with each other and exchanging energy, exchanging speeds, colliding with the walls. And on Mars, at the extreme end, the molecules that are going the fastest are actually going fast enough to escape the planet entirely into space. So that's why Mars has such a thin atmosphere today, but in the past it would have been thicker. It's also very cold on average, 44% of the Earth's sunlight, but it's just an astonishing coincidence that the Martian day is only about 40 minutes longer than the Earth day. It's unbelievable that this could be the case, and it surely demands closer investigation. It's probably just a coincidence, but you've got to think, that's amazing. Of all the lengths of the day Mars could have, the same as the Earth within 40 minutes. It's unbelievable. Also, the Martian year is about twice as long, 50% further from the Sun. And another remarkable coincidence is the axial tilt is very similar to that of the Earth. So this gives rise to the seasons on Mars, as it does on Earth, but Mars has a relatively eccentric orbit. The Earth's orbit is remarkably circular, and so the distance Mars from the Sun varies dramatically during the year, whereas on Earth it's only a minor effect. We get slightly hotter summers in the southern hemisphere when Earth is slightly closer to the Sun, but it's very little difference to the northern summer, whereas on Mars this takes a much bigger role. And also, because of this relatively large eccentricity, coupled to the pull of the other planets in the solar system, coupled to the wobbles in the Martian spin axis, it does lead to more dramatic cycles of ice ages and what have you on Mars than Earth experiences due to the same phenomena. So studying how all these things work together to give the conditions on Mars today is very useful also to feed back to understand Earth and why the Earth is like it is. But because there's very little tectonic activity on Mars, there are no plates like there are on Earth that are roaming around the surface and being subducted and pulling apart. At least it may have started the same way, but the planet seemed to cool very quickly and all the tectonic plates froze in place. This means that the surface of Mars is very ancient. Unlike the Earth, where there are just a few outcrops in the Kimberley and in Greenland, which are billions of years old, on Mars, most of the surface is 3.5 billion years old. So this means that if life got started on Mars, then maybe the relics of that are still lying around on the surface, no longer alive because of the leakage of the atmosphere to space and the harsh ultraviolet irradiation and more. But this could be an excellent place to look for the relics of the still mysterious origins of life on Earth if Mars went down the same path. As I keep trying to explain to people, Earth is the most Earth-like planet, and the probability that life evolved on Earth was 100%. Here we are. And so, if Mars was Earth-like in the past, then extrapolating from that single data point suggests life should have got started on Mars too, if the chemistry is the same. And I just found a fascinating paper published on the archive that applied Moore's law to living organisms. I just digress for a moment into the realms of what may not yet be respectable science. But Moore's law, let me hasten to remind you, is the fact that computer power doubles every 18 months as the scale continually decreases. And it's that decreasing scale that unlocked the technologies that allowed us to program the phosphorus atom that I described earlier. Intel devices now have dimensions of the order of 22 billionths of a metre, which is truly astounding. If you go any smaller, you're going to have to count the atoms because the atomic variations will be. But if you apply that to life, look at the scale of the cells and the complexity of the mechanisms in our own bodies, and you apply Moore's law to that and extrapolate back and say when was the first cell, then the answer is about 7 billion years ago, which is twice, roughly, 1.5 or twice the age of the Earth, which suggests that an origin somewhere off the planet. And therefore, if that remarkable idea is true, then our planet was seeded from outside, and therefore Mars would have been seeded from outside. And perhaps we'll find the relics on the surface still today. So that's an exciting prospect, maybe not yet respectable, but I think as we explore these ideas, the answer may come from the Martian surface. So the Hubble Space Telescope shows very nicely the ice caps and some of the surface features, but if you really want a close-up, you've got to go there. And it's now clear from all the minerals and the careful observations that in the distant past, 3.5 billion years ago, when Mars still had a thick atmosphere, a stronger greenhouse effect, and an atmospheric pressure that allowed the liquid water to exist, that there could have been oceans and rainfall and rivers on Mars. 3.5 billion years ago, and we see the relics, because of the absence of plate tectonics, still noticeable on the surface today. It's important not to get too carried away, though, in speculating about whether there was life on Mars. And I really wouldn't get too fantasise too much. But if advanced life did evolve, and that took a lot longer than a couple of billion years while the atmosphere, while the planet was drying out. Maybe there are still fossils to be found in some of the strata that Curiosity is heading for. So if we look at from the genesis of the solar system 4.5 billion years ago, we had this where there was Mars, rains and everything. Then it's like there was this period of very heavy cratering. So those craters are gone, eroded away on the Earth, but the evidence is still on Mars. As the atmosphere gradually leaks, the water disappears, evaporates into space. We get a period of very strong volcanic activity, some very weak plate tectonics, not like here on Earth where you get a hot spot in the Earth's crust and that leaves a chain of volcanoes behind it. As the plate moves across it, on Mars the plates are frozen, so the volcanoes get truly gigantic. And there was another period of volcanic activity 1.3 billion years ago, and periodic ice ages up to the present. And so in this scenario, perhaps life was seeded in the oceans of Mars, predominantly in the northern hemisphere. Then as the atmosphere leaked to space, that life was destroyed by the sun's ultraviolet radiation unless it went underground, and maybe there are some fossils still to be found. So in 1976, the Viking landers went there with the specific purpose of seeing if there was life on Mars. This was a huge mission, very expensive and very sophisticated in 1976, considering the computer power that was available then. And one of the things the landers did, they scooped up some of the Martian soil and tipped it into a saucepan full of chicken soup, or some more sophisticated analogue. And the idea was that any microisms in the soil would somehow find the chicken soup a favourable environment and multiply like crazy with all these nutrients. As you can test yourself, if you leave a saucepan of chicken soup exposed in your kitchen for a few weeks, my children do this, you'll come back and find it absolutely seething with life. And so in this experiment, there was the atmosphere in the saucepan was replaced with carbon dioxide that was loaded with carbon-14, a radioactive isotope of carbon, and it was anticipated that the organisms in the soil would start consuming this radioactive carbon and release it where it could be detected. And here's the data that was sent back, 1976 we're talking about here. So this is time on the horizontal axis in Martian days, and this is the amount of radioactivity detected given off from the soil. First of all, a sample of soil was heated to very high temperature, which was assumed to be sufficient to kill any Martian organisms. And when that was tipped into the soup, nothing happened for days and days. Clearly the soil was sterile. However, an unsterilised sample of soil suddenly started generating carbon dioxide like crazy. But then, unlike what would have happened on Earth, where it would have exponentiated up until all the resources were consumed and then it died, it plateaued out. And it was a bit surprising. So this is tantalising evidence that there was microbiological activity in this soil, but not like Earth organisms. Or it was some kind of strange chemistry from soil that hadn't been heated to high temperature, possibly containing perchlorates or other very reactive chemicals. And so today these data are being reappraised. They were dismissed as not being conclusive, but a lot of people feel this was evidence that there was some kind of life there, and maybe it got poisoned by the Earth nutrients in the saucepan instead of finding it a convivial environment. You know, too much of a good thing perhaps compared to the austere conditions on Mars. So perhaps the jury is still out on whether life does exist, at least in the first few metres of the Martian soil. So now the planet has been mapped in great and exhaustive detail. You can even get an Android app that has a Mars map built into it, which is very handy if you wake up in a strange place and you find you're not on Earth anymore, John Carter style. Be prepared, guys, you know, that's what I say. But we see, I still remember when I was a very young lad and the Mariner missions began beaming back the first images from Mars, how disappointing the images were, because I thought there'd been a terrible mistake at mission control and the Mariner had been put into orbit around the Moon, not Mars, because there were all these craters and it was it didn't look like Mars, which should have had canals and oases and green Martians. But no, it's indeed an ancient surface. And many of the craters that it has been carrying for 3 billion years are still visible, and some enormous impact basins that perhaps were oceans in the past. So this is a whole of Mars map. I'm sure many of you have seen this, colour-coded with a very suggestive colour coding for altitude. And we see remarkable asymmetries between the northern hemisphere and the southern hemisphere. The north is very flat and indicates low elevations. Because here, it's from billions of years ago, still clear, but in the northern hemisphere, they've mostly gone. So this, together with the very suggestive colour coding, suggests we're looking at an ancient sea bottom here. And this is the ancient coastline that used to have rivers running down to it. And detailed investigations of the hypothetical ancient coastline have now revealed hundreds, if not thousands, of river deltas, where rivers have clearly flowed into a sea, precipitated out all the debris that they were carrying, just like on the Earth. So I think now the evidence for this planet-girdling ancient ocean is now overwhelming. There are other mysterious features on Mars that suggest, that look like river channels, but don't withstand scrutiny, because it appears that the channel was created with a single flood, not a prolonged flow of rain creating the river and having it flow over thousands or millions of years. There's a rift valley here, the Valles Marineris, discovered by the Mariner missions, that's equivalent to the rift valleys on Earth, but on a titanic scale. And here are here's Olympus Mons, the biggest volcano in the solar system, and the chain of volcanoes from the uplift here. And there's all sorts of fascinating geological features or aerological features around those. So here's very suggestive colour coding again. The colour coding is only for the altitude, but this surely does look like some kind of giant flood of a liquid carved these channels, if not sustained precipitation and rivers. There's a colleague of mine in the Earth Sciences department at the university who proposes that these could have been made by floods caused by debris riding on carbon dioxide. He calls this a cryoclastic flow. But I think now it's more likely to have been water. But now with the new data coming back from the various satellites, you can see a lot of activity on the Martian surface, avalanches down the walls of craters, and most mysteriously, these places where, with seasonal variation, you see these dark stains appear down the walls of craters and cliffs. And these come and go. And there's lots of them peppered right across the southern hemisphere here where there are steep cliffs. And these are almost certainly water stains where, as the temperature has risen, maybe the carbon dioxide that was on the surface has evaporated, sublimed into the atmosphere, and liberated just briefly some liquid water. It could be liquid if it had a lot of salt dissolved in it, which lowers the freezing point, and then flowed down into the Martian soil to leave these stains. So that's a remarkably dynamic situation with strong evidence that liquid water can exist briefly in the Martian conditions. I'll just give you the idea of the scale of the Valles Marineris here. Spans the United States for comparison, and these volcanoes are truly titanic. Olympus Mons is 15 miles. That's an ancient unit, now obsolete, but favoured by our American cousins. Really true to Everest or even Mauna Kea measured bottom of the Pacific. So we don't have any volcanic feature of that scale on Earth. how wonderful it would be to get your mountain bike. No, okay, we'll move on. So, Curiosity, August 2012, and this next series of slides is dedicated to the M12 explosive bolt. I checked to see if I could get one of these in Bunnings, but they don't stock them. But this is one of the most ancient and reliable pieces of space technology that humans have ever invented, where you can bolt a whole lot of heavy-duty kit together, and then by sending an electrical impulse down here, the bolt just explodes and everything separates. So in order to get Curiosity down onto the Martian surface, there are literally hundreds of these things, all wired up, firing in a very carefully orchestrated sequence from some very fancy computer software that was adaptive and sensitive to the environment and ready to change the program at a split second's notice to try and recover. Things started going pear-shaped, and it all worked extraordinarily well. I think they said it took 7 minutes to enter the atmosphere and land, and it was 7 minutes of terror to the guys who did the programming and assembled the hardware. So, pretty standard thing, lifting off with a Delta rocket into the low orbit, and then spin the spacecraft up to get some angular momentum, to get some high precision in the orientation, and inject it on the Martian, on its way to Mars. So I've just got this nice video because it shows a good bit of the physics for getting this off the ground. I don't know if this will work with such a distinguished audience, but we'll give it a try. Nope, sorry. So dark here, I can't see what I'm doing with this unfamiliar keyboard. No, okay, look, I'll show you that later because I think many of you may have seen this already. So I just wanted to do a digression on the physics here for a moment because it's really difficult to get things off the planet because the problem with rockets, which has been known now for more than 150 years, is that if you're going to accelerate a rocket into space, you do it by throwing things away. Namely, you throw away the exhaust of the rocket engine. So you start off with a rocket heavily loaded with fuel, and you throw away the fuel piece by piece, and you have to carry fuel to throw away later as you accelerate until you reach the desired final speed and you're on your way to the other planets or wherever you're going. And this is a terribly inefficient process, and I'll just give you a quick derivation here. I hope you're following this. It'll be on the exam, but this actually this is rocket science. This is rocket science. Pretty simple first year physics problem: conserve momentum over small time intervals and then integrate over the entire burn time, first derived by the Russians in 1903. And at the end of the day, you observe the rocket equation, the final speed minus the initial speed, and I've put in the initial speed to make it general because the initial speed, if you're smart about where you launch your rockets from, you can pick up for free the the rotation speed of the Earth. So here in Melbourne, as you probably know, a well-educated audience, the ground is going that way towards the east at a speed of about 1,300 kilometres an hour. Okay, we know that because new things keep appearing as we head towards them as we go around the line of latitude. Now it's interesting, if you go to Singapore, the ground is going to the east at about 1,670 kilometres an hour because of the equator. You've got a lot further to go. It's about 40,000 kilometres around where Singapore is, only about 32,000 kilometres around here. And I've worried about this a lot because that 350 kilometre an hour difference is not insubstantial. And I worry with all these cheap airlines, you know, does that delta V get included in the cost of the ticket? You know, so I urge you, if it looks like a really good deal, just check they've included 350 kilometres an hour of delta V in taking you up to Singapore, because it'd be a hell of a run when you got off the plane if they didn't. Consequently, I calculated I was 110 grams lighter in Singapore than I am in Melbourne because of the centripetal force. but a quick trip to Sammy's Curry House soon fixes that. So if we look at the rocket equation here, so the initial velocity should be, you should launch your rocket as close to the equator as you can and fire it to the east, obviously, and you pick up a free 1,600 kilometres an hour. And the final velocity needs to be the escape velocity of the Earth, and this is equal to the exhaust velocity, the speed with which you throw the burned fuel away, times the natural logarithm of the ratio of the initial mass to the final mass. Now this is very depressing because the natural logarithm in here means that the mass of your rocket escalates unreasonably, or logarithmically, in proportion to how fast you want it to go. So if you want to go fast, you have to go fast to get off the planet. You've got to maximise the ratio of the initial mass to the final mass. You need a really heavy rocket and you can only put a little bit into space, and you need a really fast exhaust velocity. So you need 11 kilometres a second to escape from our planet. No smaller speed will do. And the best chemical fuels, liquid oxygen and liquid hydrogen, burn together in a good engine, escape the engine with a speed of only 3 kilometres per second, much less than the escape velocity. So you've got to burn the engine for a substantial period of time to accelerate. And when you plug these two numbers into this equation, the initial mass divided by the final mass has to be 55. So with a single stage rocket, only 2% of the mass can go into orbit. The other 98% has to be thrown away, the fuel. And when this was worked out, first people thought the space was closed to humans because there's no way we could build a rocket with better than this if we confine ourselves to chemistry, of course. Physics has since opened a lot more fuels for which this is pathetic. But anyway, we'll get back to that in a moment. So that led to the idea, okay, not only do we have to throw the fuel away, we've got to throw most of the rocket away as well. And hence the idea of staging, which was the solution that got around this very unfavourable result. And if you look at all the fuels that are available, looking for something with a higher exhaust velocity, you can see here solid fuel, homebrew. I'll show you some experiments in just a second. 1,300 metres per second. Liquid oxygen kerosene, the first stage of the Saturn rockets, 3,300. Methane is still experimental. Oxygen and hydrogen, pretty good. This has never been used. This is ozone and liquid hydrogen. This would be extremely unstable. And even better, monatomic hydrogen, oxygen and liquid hydrogen. So this is, instead of O2, this would be O1, 7,400 metres per second. The only drawback of that, if you went up to the rocket while it was sitting on the pad and did this on the fuel tank, that monatomic oxygen would spontaneously convert to molecular oxygen, and that wouldn't be good. The NERVA program, you could well, sideways probably, yeah. In the 60s it was thought we could do better. You can make a gigawatt nuclear reactor in a very small, just a metre or so diameter cylinder, pass hydrogen through it and it will come out at a very high speed. The trouble is this is an inherently unstable and extremely dangerous design because the fuel also cools the reactor. So as you run out of fuel, the heat hasn't got anywhere to go and it's very dangerous. Or a fusion plasma, no idea how to do that. But Curiosity was launched on Atlas V. It used Russian-built engines. In fact, the Russians seem to be providing most of the big engines for the American space program these days. I guess it keeps them out of mischief. And solid rocket boosters, and a second stage burning hydrogen and oxygen. So I just put this in because the NERVA rocket engine was proposed seriously for some human missions to Mars. So you have the reactor, you can see it here, quite small with the exhaust. This is mounted upside down, but they never solved the problem of how to keep the core cool once you ran out of fuel. And many of these experimental rockets suffered from meltdown of the fuel, in which case you had uranium vapour come out of the exhaust, which was not good. apart from the fact it gave an enormous surge of acceleration just before it failed. And the atmospheric test ban would prevent that being used inside the atmosphere today. And there's often controversy about launching nuclear materials into space. Solid rockets are good because they're very simple. This is a flashback to, very nostalgic to see this now, to my experiments in the early 70s. A mixture of zinc dust and sulphur was the propellant, and these things really performed beautifully, but sometimes this would happen. This was taken with an automatic camera powered by a mousetrap. Anyway, back to Curiosity. Enough of my misspent youth. So here is Curiosity being assembled, ready for launch. The rover itself weighed nearly a tonne, and it was embedded in a descent system weighing 2.5 tonnes, and there was about a half-tonne body that went around all of that to guide it from Earth to Mars. So we're talking some pretty heavy-duty machinery here. So here's the rover inside its carrier about to be mated with the heat shield, and of course all this is held together with those M12 explosive bolts, and all these wires go back to the computers to be ready to fire them at the appropriate time. Now, outer space, hostile environment, no air obviously, but also plenty of cosmic rays. So basically what happens here is that when Curiosity was on its way to Mars, its Geiger counters were recording strikes from energetic protons. And every time one of those things happened, periodically, a few times a month, it recorded these big spikes. And then it entered the atmosphere, everything separated, a parachute came out of an advanced design. The Martian atmosphere is actually too thin to descend all the way to the surface by parachute. The parachute would have to be too big. So this was the biggest parachute ever used on Mars, and then it used the rockets for the last stage. When the cruise stage was jettisoned and the heat shield was exposed and it entered the atmosphere, it had to change its balance, so it would enter the atmosphere with the velocity vector pointing out to the right here, so that the heat shield would absorb the heat. It didn't descend vertically. And I haven't got time to say very much about this, but it had to change its balance so that it had the correct orientation so the heat shield would absorb its heat. And if you're ever launching a rocket for future reference, make sure that the centre of pressure, which you can obtain by cutting out a silhouette of your rocket and finding where it balances, lies behind the centre of gravity, which is where the rocket itself actually balances. Because if the centre of pressure is below the centre of gravity, the rocket will fly stably and be self-correcting. If the centre of pressure is above the centre of gravity, the rocket will flip over and anything could happen. So as Curiosity came down through the atmosphere, it actually had to jettison 6 tungsten weights, 25 kilometres each, to adjust the relative position of the centre of gravity and the centre of pressure to ensure a stable trajectory through the atmosphere. And those 6 tungsten weights then formed artificial meteorites, and the craters can now be seen from space when they eventually landed. And so here's the centre of pressure, just in the middle of the silhouette, and there was the centre of gravity with the tungsten weights down here to get the right orientation. So 6 artificial craters with tungsten vapour in them. So big heat shield, several megawatts per square metre of heat dissipated, slowed it down to twice the speed of sound, popped the parachute, and the parachute was actually captured from orbit, and this is a remarkable image of a spacecraft observing another spacecraft descending to the atmosphere, and you can even see the heat shield lying on the surface over here as it went down. Close up, very nice, with the Gale crater in the background. And then once the parachute had done its job, it was jettisoned and it descended the rest of the way by rocket. These were hydrazine thrusters. Hydrazine is an excellent monopropellant. It explodes violently in contact with a catalyst and generates an enormous thrust. So there was about half a tonne of hydrazine on board for this last stage, with the rover dangling precariously underneath on a piece of rope that looks like it did come from Bunnings. And then when the wheels touched the surface, the rope was cut with a special explosive knife, and the engines were throttled up to maximum, and this flew away to a safe distance where it crashed. And the crash was recorded from the cameras on the Curiosity lander sitting safely on the surface. And if you look down from space, you can see the lander. You can see just barely on this image the disturbance on the Martian surface from the hydrazine exhaust as it sort of drifted across and touched down with a final burst disturbing the Martian soil. And now from space you can see all the debris lying around. So you can see where the descent stage crashed, some other fragment over here, the parachute flapping in the breeze, the rover itself, and the heat shield over here spread over several kilometres of the Martian surface. I don't know whether the EPA has anything to say about all this garbage, but valuable souvenirs. Down in the future, down on the surface, the cosmic ray strikes continue to hit the aircraft, and because the atmosphere does not block them like ours does, and you still see big spikes from high energy protons passing through the electronics. So the motherboard is very fancy. It has to be capable of withstanding the upsets caused by a high energy proton passing through the microelectronics. This is therefore what causes the human view to be different to what you see in this camera image. I've interviewed a number of astronauts about this, particularly guys who have been on long duration missions on the space station, and they do report seeing this phenomena where you see flashes of light from cosmic rays passing through your eyeballs when you're in space. They said it's not much of a problem during the day, but it is a bit of a problem when you're trying to sleep, and flash all the time as the protons pass through. I don't know how often you would see it, probably 2 or 3 times a day maybe, but it is something that would be a bit strange compared to our experience on Earth. I've tried to look for this myself. I don't go into space very often, but I do go to the edge of space very often by flying 10 kilometres above the surface of the Earth. This is my trip to the Chinese city of Harbin last year. I always like to take a Geiger counter with me when I travel. And by putting it in my bag and putting it through security, and it gets a huge dose of X-rays, as you can see here, Melbourne security. And then as the aircraft descends 10 kilometres above the Earth, above the shield of the atmosphere mostly, the background radiation becomes enormously intense. There's an effect where the magnetic field suppresses the radiation around the equator, so it falls off as we cross the equator and then began to rise. I descended into Shanghai, changed planes, flew, and Shanghai security, those guys don't mess around. They've obviously got the X-ray machine turned to maximum compared to Melbourne, and then up to Harbin, and the background radiation in Harbin is much higher than it is in Melbourne. It's not much point trying to explain this to your fellow passengers, I've found. They're just not interested. But anyway, down into the Gale crater, I just want to zip through to a couple of the highlights here because I've used up my time now. Curiosity, so big, a lot of electronics, big motors, solar power is... Sorry? That's it? Okay. Oh, it's a phone. Oh, right, okay. Too big for solar panels. The solar panels are too feeble on Mars for a big craft like this. So Curiosity is powered by a nuclear thermoelectric generator. You can see this thing sticking out the back. It's basically a pellet of plutonium oxide surrounded by the infrared equivalent of solar panels. And they take the heat, convert it to electricity, and that's what powers all the instrumentation. So it can operate 24/7, or I should say 24 and 40 minutes 7. Also, the waste heat is circulated in tubes carrying ammonia around the rest of the craft to keep all the electronics and the joints warm so that it operates at the optimum temperature. And this will go for a long time. The Russians pioneered this, used them to power lighthouses along the Arctic Ocean. But not exactly best practice in the way they're managed. On board, there's a lot of instruments for detecting buried water, of which we see evidence also from space. And these consists of a neutron generator that blasts neutrons down into the surface from one side and picking up the neutrons scattering back out of the surface, and they scatter most prominently from hydrogen attached to water molecules. So the amount of neutrons scattering back tells you how much water there is in the soil, and it turns out there are lots. There's also this APX spectrometer. This is a very fancy piece of kit here. It's got a radioactive source that generates copious alpha particles. This is touched on a rock. The alpha particles go into the rock and induce X-rays. Characteristic X-rays which come pouring back out, and they're detected, and you get an X-ray spectrum, and each peak corresponds to a different element in the crust, in the rock. And so this is a very direct and simple way of measuring the composition of the rocks, and it's used here on Earth routinely by the CSIRO and the people down at the synchrotron. And this is a very nice instrument. The way it works is that an alpha particle comes in and knocks out an electron from the inner shell of the nucleus, and then the vacancy is filled by another electron decaying down, and the surplus energy appears as these X-rays, and they're characteristic of the atom. Jeff Moseley discovered this in 1910 in his laboratory in Cambridge, and this sorted out the periodic table. A few years later he was sent to Gallipoli and was killed by a sniper's bullet, a tragic loss. He would have got the Nobel Prize. I do it in my lab in Melbourne using a big particle accelerator, and this was an Aboriginal bead found in an Aboriginal midden, which we analysed, and you see the same peaks from the different elements. So lots of things. There's a laser for vaporising the rocks, and there's an X-ray spectrometer to look at the crystal structure. And just in the last few weeks, they've released data on this, what clearly looks like a sediment from the bottom of what was an ancient lake in the Gale crater. And when you feed it's drilled up some of the soil, some of the rock, some of the sedimentary rock, put it into the spectrometer, and when you heat it up, what comes off? Huge amounts of water vapour. So this soil is highly hydrated. So this is a relic of the ancient lake that used to exist there. So from the landing point, Curiosity's headed over here, where there's a junction between three different soil types. So this is a scientific bonanza, this particular zone. I think we'll see a lot more interesting results come out in the near future. So what then of the more distant future? Well, we'd like to get some Mars rocks back here to look at more closely, but this is a very challenging task. And perhaps one day we'd like to send people there. And even if you're a fan of Kim Stanley Robinson, with some judicious engineering, we could perhaps liberate the soil and the water from the soil, the carbon dioxide frozen into the ice caps, and one day we could return Mars to how it was 3.5 billion years ago. I don't think we should do that. We should celebrate Mars for what it is in its natural conditions and don't tamper with it. And above all, if there are Martian organisms there, don't contaminate them with Earth organisms until we understand doing. And one day in the future we might overcome the limitations of the primitive chemical powered rockets that we're using now, and this is a Project Orion that ran for 10 years in the early 60s, which the rocket equation could be bypassed entirely with a much more powerful form of propulsion based on fission. And Freeman Dyson was one of the architects of this, and the minimum size of a spaceship to go to Mars suitable for this sort of propulsion was 4,000 tonnes. And in fact, this sort of rocket scales unlike a chemical rocket. If you had a spaceship that was perhaps more like 100,000 tonnes in mass, then the fuel would only need to be about 5% of the total mass. So this is a really major game changer. The designs are on ice, available for the future, and perhaps one day, and it could have been built with 1950s technology, and one day perhaps those plans will see a new life if we discover another planet-busting asteroid heading our way, because it's the only thing we could assemble fast enough that would be powerful enough to do anything about saving the planet. And it will happen, but who knows on what time scale. Our planet has periodically been hammered by these huge asteroids. The only certainty is that it will happen again. We're not sure when, but we'd like to do something about it. This could be the answer. Thanks very much for your attention.